If you spend a lot of time in industrial automation, you probably run into the same frustration. The machines want to talk, but getting that information out from the machine and then being able to do things with it, well, that's quite a bit more complicated than just plugging it into the system. This is especially true when you don't just want to monitor that data, you want to work with it. And what if you want your data to have more context, more semantic meaning? Well, that suddenly makes the problem even more complex. Hey there, my name is Christopher Sandoval. I'm the Developer Relations Advocate here at FlowFuse. And today we're going to talk about a possible solution that solves these problems for you. So let's dive right into the why, the what, and the how of OPC UA. What is OPC UA? So OPC UA stands for Open Platform Communications Unified Architecture. And it's an industrial communication protocol that was standardized as IEC 62541. It's a very catchy title, but don't let that fool you. This is actually a really interesting protocol. See, OPC started in 1996 as a Windows-only specification that was built around Microsoft's DCON technology. And it was later broken into subcategories like OPC DA, OPC HDA, and OPC A&E. Now, OPC Classic worked, and it still works today in a lot of plants, but it had a fundamental problem. It was chained directly to Windows. You couldn't just run it on a Linux server or on embedded ARM devices. Basically anything that wasn't a Microsoft stack just didn't play well with the technology. In an industry that runs on 30-year equipment life cycles, that's a huge limitation. In 2006, the OPC Foundation released OPC UA, the Unified Architecture. Now, the word unified is doing a lot of work there. OPC UA consolidated all of those separate classic specs into a single platform-independent framework. It could run on Windows, Linux, Mac OS, microcontrollers, cloud services, and everything in between. It uses TCP as its primary transport, and it has an optional HTTP/HTTPS path for web-friendly environments. And more importantly, it introduced something that OPC Classic never had, a standardized, extensible information model. And this is where OPC UA gets really interesting. When most people hear about it, they think that it's just another communication protocol. When they hear OPC UA, they think Modbus or Profibus or DNP30. And you can certainly use it that way, but that's not all OPC UA actually is. In fact, OPC UA is best defined as three things all at the same time. An information model for describing what the data means, a service set for reading, writing, and subscribing to that data, and a security framework that's built around it, not bolted on after the fact. And that combination is fundamentally what separates it from other options. Why OPC UA? So let's talk about why OPC UA might be a good solution in practice. Rich metadata, data that describes itself. First of all, OPC UA is a standard that describes itself. Consider for a moment your realities. In the first, your factory historian receives a message, temperature 74.3. In the second, it receives a reading from an OPC UA server that tells you the value is 74.3, the data type is double, the engineering unit is degrees Celsius, the node identifier is NS equals 1, S equals boiler temperature, and the quality code is good. There's also a source timestamp when the sensor actually measured the value, and then a server timestamp when the server processed and forwarded that information. Now that's the difference between a measurement and information. All of that additional information allows you to understand the context of that data when it was generated and when it was parsed. In the first example, you have to have everything downstream able to either parse the metadata or extract the metadata from some other service. With OPC UA, all of that information is given as part of the data itself. It's self-described. Now that eliminates a ton of ambiguity, but it also gives a canonical reference that you can use to then go get more information about that data. OPC UA is much closer to a hypermedia engine of state kind of solution than it is just a simple reporting protocol. You can not only get the information, you can get metacontextual information about the information, and then you can find out exactly where to get more information. Security that's not an afterthought. Now, OPC UA as a solution has three security modes baked in. There's none, sign, and sign encrypt. None is exactly what it sounds like on the tin. There's basically no security. But in sign mode, these messages are digitally signed. And that means that any tampering is actually detectable. That's great for any sort of chain of custody that you need or any high security data transit. Going a step further in sign and encrypt, the full session is encrypted on top of that. And that matters enormously in the context of OT security. OT networks were historically air-gapped, and that meant that security was largely a physical concern. As long as you controlled access to the plant itself, you were pretty much okay. But as plants have modernized and connected OT networks to IT systems, and then those to cloud infrastructure, that air gap has pretty much disappeared, and with it, that level of security has diminished. OPC UA was designed exactly for this purpose. a shared language for machines. Now, OPC UA critically defines something called the address space. The address space is a hierarchical namespace of nodes, and every piece of data, every piece of equipment, every method or event on an OPC UA server is represented as a node in that address space, with a stable identifier called a node ID. Now, what makes this powerful is that with companion specifications, things like Euromap or OMAC, you can extend the base address space with standardized models for specific domains. That means there's a companion space for robotics. There's one for CNC machine tools, one for plastics machinery, one for MBIS. When two vendors both implement the CNC companion spec, a client talking to either of those machines can discover and interpret the data structure without any additional infrastructural work. And that's a huge step towards something like cross-machine interoperability. And it's fundamentally something that protocol-only solutions like MQTT just can't do. In most cases, a transport protocol is just doing the transportation. It's not providing any context or any structure. Efficient push-based subscriptions. Now, OPC UA has a publisher and subscriber modality. What that means is that you can have a server say, hey, I have this information that I can publish as a temperature read. And then on the other side, you can set up a client that says, hey, I want to subscribe to that information. The server then pushes notifications only when those values change, at specified intervals, or when you trigger a call. And that's super bandwidth efficient and latency aware. For a variable like a production counter that increments every few seconds, subscription-based modalities mean that you're getting every change without unnecessary polling overhead. For a variable like machine state enumeration that changes infrequently, you're not wasting network capacity sending the same value over and over again. And that, with all the other additional meta-contextual information, gives you the ability to send sparse amounts of data while still communicating a ton of information. Platform independence and vendor neutrality. Now, this is a huge one. OPC UA is a vendor-neutral implementation. There are certified server and client implementations for C, C++, Java, Python, .NET, Node.js, Go, and Rust. The OPC Foundation runs a certification program so that products carrying the OPC UA logo have actually been tested for interoperability. A certified Siemens OPC UA server and a certified Rockwell OPC UA client should, in principle, be able to work together out of the box. For system integrators and plant operators who are managing equipment from a dozen different vendors, that interoperability baseline is worth a lot. And with a system like FlowFuse, you have a whole host of options for how to connect to those OPC UA devices. That means that you can move faster and make more intelligent systems with less effort. How it all works. So with all of that in mind, let's look at how this actually works. Now, if you'd like to build your own OPC UA flow, this is the node that I'm using right now, node-red contrib OPC UA. And what this gives you is a whole bunch of OPC UA nodes to bring into the workspace. Now, it's important to understand that OPC UA needs you to actually define things. This isn't like MQTT where you're just pushing everything out and everything is fine. You actually have to give it some sort of information. Now, as you can see, I'm pushing all of this data over MQTT. But in order to push it to OPC UA, I need to give it a little bit more context. So in this function node, I'm doing a few things. I'm giving it a name, a data type, and I'm basically structuring it so that I can push all of this to OPC UA. Now, that's a really important aspect of this technology. You need to actually have the data type registered, you need to have the namespace identified, you need to know the structure that you want. So for instance, if I'm pushing over temperature information, then I'm going to use this piece of code to put it in namespace 1 with the name temperature and the data type double. And then from there, I'm giving OPC UA an actual command, which is to add the variable. If you want to look at this code directly, you can go to the link in the description below to find our GitHub. So once this data is contextualized, we're then pushing it through OPC UA itself. Now, the best way to think about the OPC UA server node is to think about it as the out pathway. Once you've defined all of your information, you need to actually push it to the server itself. And in this case, we're using a local OPC UA hosted on localhost with port 54840. Now, this is a really critical aspect of OPC UA to understand. If we compare it to something like MQTT, MQTT is basically just a transport protocol. It's sending out information as the information is being generated, but it's only unidirectional. Put another way, we can send messages out, but we can't really send anything back. If we need to send the message back, we have to do MQTT on the other side and have the client that emitted the original messages subscribe to this new broker to get its instructions back. But OPC UA isn't like that. What you see here is the actual way that we're interacting with OPC UA itself. If I want to say read the temperature, then I simply click this inject node. Now what this is doing is using message topic to emit the thing that we actually want the information from. So in this case, we're identifying the namespace, we're saying we want to get temperature back, and we're expecting the data type to be double. And here we get our value back. So far this is pretty standard. You're just requesting information and you're getting it back. But what if we actually wanted to elicit a change? Because OPC UA is bidirectional, we can actually send as well as receive. So we have the same exact flow set up to read our machine state, and that's just going to tell us whether or not the machine is running. Now what we can do is send a payload as a boolean true or false, and then build the write based upon that. We can say, hey, message action write, the topic is namespace 1, machine on, and the data type boolean, and then we can use the OPC UA client node to actually write that information back. Now this isn't the only thing we can do. We have a ton of options with OPC UA, as you can see on the screen. Well, let's just go ahead and write machine off. So let's send turn machine off and see what we get back. As you can see, we get a status code which says good, which means that we've actually written this to our OPC UA server. And then if we read it again, now we get false. The machine is no longer running. Now this might seem rather simplistic, but the real benefit here is the bidirectionality and the meta context around everything. By being able to write to machines, you can basically do anything. In a biomedical facility, you could have a centrifuge reaching too fast of an RPM result in a downtick in your motor. You can have energy regulation. You can have alerts and detections, automatic safety stops. You convert your systems from just communicating about the thing to being able to actually interact with the thing. You have everything here from methods to writes to discovery. You have all sorts of ways that you can interact with this data in very, very complex ways. And that makes it more than just a transit protocol. It takes all of your machines and connected systems away from purely recording data and creates a living organism that you can directly interact with. Looking to the future. So OPC UA is not a new technology. It's been around since 2006, and in industrial terms, that's actually a sign of maturity, not age. The specification itself has continued to evolve. The broader trajectory here is towards what the industry is calling the smart factory, or Industry 4.0 architecture, where every device in the plant, from the enterprise ERP system down to the field sensor, shares a common information model and a common security framework. OPC UA is then fundamentally the standards layer that can make that architecture coherent. That said, it's worth being honest about its complexity. There is something to be said for how complex OPC UA is compared to something like MQTT. Now that does come off with significant trade-offs in their capability. OPC UA will give you a ton of information, but it is a lot more complicated to set up, and it does take time to get working properly. Tools like FlowFuse make the protocol accessible to developers who aren't OT specialists. If you're building industrial IoT systems, or you're managing the integration between OT and IT environments, you understand that these environments are exceedingly complex. FlowFuse not only gives you the ability to build once and then deploy over and over again, it gives you a trustworthy and sound base from which to develop your OPC UA systems. Not only is your transit protocol secure, the actual systems underlying it all are secure as well. And although OPC UA can be somewhat complicated to get started with, there's ample documentation both on the community side and on the official side to get you going as fast as possible. We hope you liked this video. If you did, please consider giving us a like, comment, or subscribe. And if this piqued your interest for OPC UA on FlowFuse, then head on over to flowfuse.com to start your free 30-day trial. And if you'd love to learn more about options like MQTT in comparison to OPC UA, then check the link in the description below for our upcoming webinar on this topic. I'm going to be joined by Senior Industry Solutions Advocate Kudzai Monteteresa from HiveMQ as we dive into the differences and similarities between MQTT and OPC UA, as well as some practical examples of where they can be deployed together. This has been Christopher Sandoval. Thanks for watching, and I'll see you next time.